Let us quickly imagine a situation. We have a square table here, and on top of it lies a square glass, perfectly fitted. So the edges of glass and borders of table are perfectly aligned on each side. But over the time, a layer of dust has settled on top of glass, also under the glass. And today we decide for a cleanup. So we lift the glass, be careful, huh? And with a brush or a cloth, we wash away all the dust from each side of the glass. And now we are about to place the glass on table. But wait, we could place how it was exactly on the table. Or we could rotate it by 90 degrees and place on the table and it would still fit perfectly. Or we could flip the glass vertically and it would still fit perfectly on top of glass, on top of table. So our point is, we'll see all those motions which fits our glass on top of table perfectly. A rotation of 45 degree will not work because some part of the glass will be outside the table and some part of table will not be covered also. So we are caring about the motions which fixes our square as it was on the table. And the interesting part is all these motions which puts our square glass on top of table perfectly forms a group under some of this. And in this video we'll see this group. Let's see. So this is our square glass. All sides are equal and the angles are 90 degrees. You all know what a square is. And we are interested in all possible rigid motions that puts our square back into the space it originally occupied. So we are interested in the all rigid motions that puts our square back into the space it originally occupied. So rigid motions means translation. Translating means you will move the object. Translating. Rotation, we will rotate the square. Reflection means we will flip the square in some excess. And what are not allowed things are stretching, compressing or tearing. These are not allowed. We are not allowed to do all these things. We are not going to tear the square and change the square back. Stretching, compressing, these are not allowed. And what are allowed rigid motions are translation, rotation or reflection. If after some motion we are getting our square like this, this is also not required position. We want our square as it is. We want our square as it originally was. So this is our required position and this is not required position. Not required position. This is required position. Now we'll see all possible motions that puts our square back into its original position. So this is our original square, and for easy tracking of corners, we'll label the corners. Suppose this one is 1, this is 2, this is 3, and this is 4. We can label any letters or any numbers and in any order. It doesn't matter. The first thing is we can put exactly how it was. So first motion is do nothing. We can do nothing and put exactly how it was. And by doing nothing, we'll get our square back, because we are not doing anything to our square. So square will. And second, so this one is our first motion. Second, let me draw smaller squares, and we have to draw all these motions. And this is 1, this is 2, this is 3, 4. Next we will rotate the square. We will rotate by 90 degree anti-clockwise. Anti-clockwise. You can rotate it clockwise, but rotating 90 degree will fix our square. This square will be rotated 90 degree. So this side will come to the bottom, and this one will come to right side, and so on. We will get our square back. And the corners, 1 has moved to this position, and 2 to this one, 3 to this one, and 4 to this one. So corners have changed their positions. Third one, this is our original square, and these are 1, 2, 3, 4, and next we will rotate by 180 degree anti-clockwise. We will also get our square back. With the corner 1 will move to this side. So 1 will move here, and 2 will move to here, 3 and 4. Fourth one is will rotate by 270 degree. Rotate by 270 degree anti-clockwise. We'll get our square back. Rotation of 270 degree is 1, 2, 3, 4. These are our original square, and these are our square we are getting after the motion. And 1 will move to here after 270 degree rotation. 90 degree, after 90 degree 1 will be here, after 180 degree here, and 270 degree here. And similarly 2 here and 3, and here is 4. So what about 360 degree rotation and other rotations? See, if we will do 360 degree rotation anti-clockwise, so this is our square, 1, 2, 3, 4, and rotate by 360 degree anti-clockwise, and we will get our square back. But the thing is, 1 will be here, 2 will be here, 3, this is 2, this is 3, this is 4. After 360 degree rotation, we will get our square as it was. It is like doing nothing. We are interested in the net effect. So two motions will be same if the net effect on the square is same. Let us write that two motions are same if the net effect on all the points are same. So if we are doing two motions, suppose this is one motion, I am moving the square by 90-degree clockwise, and this is exactly same as rotating the square 270-degree anti-clockwise. The points of the square after 270-degree anti-clockwise are exactly in the same position if I rotate the square 90-degree clockwise. So these repeating motions will be treated as one. We are going to treat them as single motion, and let us name them. This is, suppose this is R90, and this is R180, this is R270, and this one has rotation of 0-degree anti-clockwise. 0-degree rotation means we are doing nothing. This is R0, this is R90, this is R180, and this is R270. So we have four rotations, and any other rotations you will see those will either repeat our motion or they will not fix our square. Next we have reflection. In reflection we have four reflections, and we will see all them. First one is, this is 1, 2, 3, 4 original square. First one is about horizontal axis. Horizontal means parallel to our ground, and this is reflection about horizontal axis. So this is our horizontal axis. We are going to flip the square. So after flipping the square, we'll get our square back, and this corner will move to here. This is our 1, 4 will be here, and this is 2, this is 3. So this is a reflection about horizontal axis. We'll name this as H. You can name this any letter. And next we have 6. Let me erase this one. So two motions are same if the net effect on all the points are same after the motions. Next we have, this is our original square, and reflection about vertical axis. Vertical axis means perpendicular to ground, and this is rotation, a reflection about vertical axis. And after this reflection we will get our square back, because we are just flipping. This side will come to this side, and this side will come to that side. We are flipping the square, and 1 will be here, 1 will go to here, 2 will be here, and this is 3, this is 3. This is reflection about vertical axis. Name this as B. So this motion is B. And 7 we have our original square, 1, 2, 3, 4. Also we can flip the square diagonally. This is our main diagonal. We will get our square back, and this corner will go to this one, and 1 is at the same position, and corner 3 is at same position. So this is 1, this is 3, and 4 will be here, this is 2. And this is reflection about main diagonal. Reflection about main diagonal. Main diagonal. And let us name this motion as D. We have this is 1, this is 2, this is 3, this is. We will flip the glass or the square on other diagonal. This is reflection about other diagonal. And we'll get our square back with the corners 2 and 4 in the same position, and 1 will be in here and 3 is here. So this is reflection about other diagonal. Let us name this as D dash. So these are possible motions because we have 8 final position of the square, and every other motion will be either any one of these, or we will not get our square back. We will get a rhombus or anything else. See, we can note this. We can have at most 8 possible final positions, because the reason is this corner has 4 choice, isn't it? We can have either A or B, not A. We can have either 1 or 2 or 3 or 4. So we have total 4 choices for this corner. And for 1 we can have 1 up or 1 down. Treat this as a square glass. For this corner we have 4 possible choices. And for any corner we have 2 possible. We can have the 1 up or 1 down. So this is 2 and these are 4. So we are getting 4 times 2, total 8 positions of this corner. And this corner will decide every other corner. So if we have 8 choices for this corner, so we will have 8 possible final positions. So these are only possible motions we can have, and every other motion will be any one of these, or will not get our square back. Let us consider all the motions we have got. R0, R90, R180, these are rotations, 90 degree anti-clockwise, 180 degree anti-clockwise, this is doing nothing, 0 degree rotation. R270, H is horizontal flip, vertical flip, flip about main diagonal, this is other diagonal. We will give one operation to this set. Operation is composition. This is our operation is composition, or we can say followed by. That means suppose we have 2 elements A and B, they will be operated as B followed by A, or we can say do first B, then A. And we are saying this as composition because in function composition, this as in function composition, we used to do first G then F. G is followed by so any two elements of this set will be operated by this one. If I am taking A and B, I will first do B, then we will do A to the result we are getting after the motion B. Let us see, suppose we are taking R270 and let be this is D, R270 and D, and this will do what? Do D first, then R270. So this is our operation. We will do D first, then R270. This is our original square, and we have labeled this one as 1, 2, this is 3, this is 4. We will first do D. D means flip with the diagonal axis. We will flip this square about the diagonal. This is our square. We are doing D first. So 1 and 3 are fixed. 2 goes to here and 4 is here. So this is our D. Then the result we are getting, we will do rotation of 270 degree anti-clockwise. So this will be rotated 270 degree anti-clockwise. So after 270 degree anti-clockwise rotation, this one will be 90 degree after 90 degree it will be here 1, after 180 degree it will be here, and after 270 degree 1 will be here. 4 will move to 90, 180, 270. Here we will have 4, 2 anti-clockwise, 90, 180, 270. Here we will have 2 and 3 anti-clockwise, 90, 180, 270. Here we have 3. So this is our operation of two elements R270 and D. We have done D first, then R270, and see what we have got. This is our original square. 1 and 2 here, and we have 4 and 3 here. So this is like doing vertical flip, isn't it? If we will do vertical flip to this original square, we will get 1 here, 2 here, and 4 here, and 3 here. This is the same as that one. So this is R270 and operated with the element D. Let us do another. Let us take H and B. Suppose we will do H and B. Here we will have to do B first, then the motion H. Our original square we have labeled 1 here, 2 here, 3 here. This is 4. And I will do B first. Flip the square vertically. This is our vertical axis. And after vertical flip, I will get 4 here, 3 here, 1 here and 2 here. Then I will do horizontal flip. So this is horizontal axis. After horizontal flip, I will get 4 here and 1 here. Here I have 2 and this is 3. This is our original square. And see, we have rotated this one by 180 degree, isn't it? 1 is here and 2 here, 3 here, 4 here. So this is R 180, and this is same as our H and D. And now we know how to operate two elements of this set under our operation function composition. And now we will do KLA table of this set under this operation composition. KLA table of this set under the operation of composition. KLA table or operation table. We have lines, and here we have the elements. This is R0, R90, D, then we have D dash. And I have the Kle table with me, and here we have R0, this is R90. So we are actually operating, this is our A and this is B, and we are operating B first then A, as we have said. And we have seen R270 with the operation with the element D, and R270 D gives V. So here we have V, and H with V we have R180. And you can fill this table on your own, you don't have to memorize. So this is our Kle table of our set of motions and with the operation of composition. First one, the operation composition is closed, because the entries of Kle table, the elements we have here are the elements of our set, and we have not got any outsiders. All these elements are in our set. So the operation composition, the composition is closed. From this operation table, you can see that R0 is our identity. Then see this row, the row of for R0, we have elements exact copy of the headers. This is R272, H, H, B, B, D, D, D dash. So R0 is a possible candidate for identity, and that happens for the column also. These are repeated. These are exact copy. R270, H, H, B, B, D, D, D dash, D dash. So R0 is our identity here. R0 is the identity. And third one, if R0 is the identity, we can check if the elements has inverse or not. Inverse of R0 is same R0. R0 operated with R0, we will get R0. Inverse of R90, let us see the column row of R90. R270 gives R0 identity. Also R270 with R90 gives identity. So in both way, if we operate R90 with R270, we will get R0, the identity. So inverse of R90 is R270, and inverse of R270 is R90. Inverse of R180 is itself, because R180 when operated with R180 we have R0. Inverse of H is H, and it is understandable. If we will operate horizontal flip with H itself, so we are doing horizontal flip twice, and this is first one, horizontal flip. Then again we are doing horizontal flip. So at the end we are getting the same square that originally we had, with the corners in the original position. So inverse of H is H. Also inverse of any flip is same. Inverse of D also D. Inverse of D dash is also D dash. Because when we are flipping and again we are flipping in the same axis, we will get our original square with the corners exactly as in the original position. Every element of the set under the operation of composition have inverse. And next we will only check the associativity. Pause the video to note. And note one thing, if you are taking rotations clockwise, then the entries here you will get different entries. because clockwise 90 is same as anti-clockwise 270. So the entries will vary if you change your direction of rotation. So don't be confused there. And you can take, we have 4 rotations. You can take 2 anti-clockwise, 2 clockwise rotations. But you will get confusion there. So to avoid confusion, be consistent with your rotation. You will either take anti-clockwise or clockwise, and flips are horizontal, vertical, diagonal, and main diagonal. Associativity. And remember, our aim was to show this is a group. For associativity, you have 2 options. This is a finite set, isn't it? We have only 8 elements. And for associativity, we have to check A, B, C, this is same as this one or not. For all A, B, C, you have 8 options for A, 8 options for B, 8 options for C. Total number of options you have for ABC is 8 cube, so which is 512. For ABC, I have 512 choices. I can take one by one. I can check if this is same as this one or not. Or we can treat our motions as functions on the labeled corners. I have taken 1, 2, 3, 4. If you have taken letters, then you will write those letters. We can treat our motions as functions on this set. What I mean is, suppose I have 90-degree rotation. This is our original square. 1 here, 2 here, 3 here, 4 here. I am doing R 90 anti-clockwise 90 degree. Then I will get 1, 2, 3, 4. And this motion can be treated as function. And that function is, this is our domain set, this is our codomain set. We have 1, 2, 3, 4 here, 1, 2, 3, 4 here, and 1 in the position of 1 we have got 4. So 1 is going to 4, and in place of 2 we have 1, in place of 3 we have 2, in place of 4 we have 3. So this is our function R90. Another, suppose this is our horizontal flip. This is 1, 2, 3. This is 1, 2, 3, and 4. We are doing horizontal flip. After horizontal flip, we have 1 here. This is 2. This is 3. And this is the same as the function 1, 2, 3, 4 domain, 1, 2, 3, 4 codomain. 1 goes to 2, 2 goes to 1, 3 goes to 4, and 4 goes to 3. And this is our function h. So the motions we have taken, I can treat them as functions on the labeled corners. I have taken 1, 2, 3, 4 as the corners. So any motion can be treated as functions, and we know. So we have composition, identity, and inverse of every element. And we know we have composition of function. Composition of function is associative. We know this. If you have 3 functions, and this is same as, so we have associativity with this operation composition, and we can note the operation. Therefore Therefore, the composition operation here is associative. Operation here is associative. So we have shown composition operation is closed. We have identity. We have inverse of every element and associative. So it satisfies all four group axioms. Therefore, this set we have with the operation composition forms a group. And we have this set R0, R90, R180, R270, H, V, D, V dash. This set under operation composition forms a group. And this group has a special name. This group is called the dihedral group of order 8 or symmetry group of square what is order 8? Name is dihedral group, and order means the number of elements in the group. Order of a group number of elements in a group. Order of group means number of elements in a group. For example, suppose we have the set of integers under addition. The number of elements in this group is infinity. So this is an infinite group and order is infinite. We have Zn our group. And what is the order of this group? This group has elements 0, 1, 2 up to n minus 1. So the order of this group is n. So order means number of elements in that group. And we have 8 number of elements. So this is a group. Name is dihedral group of order 8. Or we can say symmetry group of a square, and the elements we have obtained R0, R90, R180, R270, H, V, D, D dash are called symmetries of a square. Symmetries of a square and this group has a special notation. This is a special group. This group is denoted by D4. This is the dihedral group, the group obtained. The dihedral group of order 8. Some denote this group as D8 and many books denote this group as D4, and 4 stands for the number of sides of the polygon we have. We have 4 sides. This forms a group, and this group belongs to a happy little families of groups, and those groups are named as the dihedral groups, and this happy little group is a member of that family. And in the next video we will see the dihedral groups. till then, thank you.